In this review video, we're going to look at radicals. Now, a quick example here, just to remind us when we're talking about radicals, what we mean is, for instance, the square root of 4, which of course we know what that is, which it's just equal to 2. And then also, we have more than just square roots, we have radicals of all sorts of powers. If you have a radical with 3 and then 8, this would be, of course, the cube root of 8, which again, what number to the third power gives you 8? It's also 2. And we can keep going on here, but I'm not going to do very many examples with the numbers. I'm going to just talk about some properties here with some radicals, things that you may remember or may not remember. First thing I want to talk about is what is allowed here. So if we're looking at here just the square root of x, or even, let's say, the 4th root of x, or the 6th root of x. These all have something in common. What do they all have in common? So they all have in common is that the root is even. Because remember, with the square root, even though there's no number right here, we think the number there is actually a 2. So we'd actually have a 2 sitting right there, which you can't hardly see. So we'd have a 2 sitting right in there. But we don't write that 2, but that's what it was with square roots. So the important thing here to remember, and we'll talk about this later in the semester, but if you do square roots or 4th roots or any kind of it's even, x has to be greater than or equal to 0 in order to get a real answer. Now, I'm emphasizing the fact that it's a real answer because we will be talking later in the semester about complex numbers and the term imaginary. It's actually a very important, very useful tool in later math classes, and we'll talk about that. And when that comes about, we'll be able to do square roots of negative numbers. But the one thing I want to point out here is that just because we have to be concerned about x being greater than or equal to 0 for like the even powers, when you have an odd root, for instance, cube root of x, 5th root of x, so on and so on. Of course, these all have what's in common. The root is odd, and x can be any real number. And a quick example to kind of illustrate this, let's go back to the cube root of 8. So we have the cube root of 8, which we wrote up before, which we said is equal to 2. And again, the reason we say it's equal to 2, and we know that, is that 2 to the third power is equal to 8. But now I said we don't have to worry about negative numbers with odd roots. So if I do the cube root of negative 8, this is actually equal to negative 2. And again, the reason is that if you do negative 2 to the third power, you get negative 8. That's why we're okay with these odd roots, because an odd number, a negative number to an odd power is still going to be negative. Alright, so that's just to kind of remind you about even and odd roots. Now, let's look at an example here of something that we're also hopefully familiar with, and this is rationalizing. This is going to be a very useful skill, not just in algebra, but if you go on into trig or into calculus, rationalizing is going to be a concept or a tool that you'll use quite often. So let's just do a couple quick examples. There's kind of what I would say two basic types here, and I'm going to emphasize here that we're going to rationalize the numerator in these examples. Now, the reason I'm emphasizing that is that technically we don't have to rationalize the numerator. We could rationalize the denominator. And right now you might not understand why you would ever want to do that, but it turns out in some later math classes that's actually useful, is rationalizing the numerator as opposed to the denominator. So let's go ahead and look at this here, and we'll also do a rationalizing the denominator as well. So let's look at 5 square root of 3 over So if we're rationalizing the numerator, what that means is we want the numerator should contain no radicals. So with this particular one, the easiest way to do this is you'd have 5 square root of 3 over 2, and we're going to use a property of algebra, which is a very common one we use, which is if you multiply the numerator by a number, as long as you multiply the denominator by the exact same number, you haven't changed anything. And in this case, we'll multiply by the square root of 3 over the square root of 3. And clearly we can see why that doesn't do anything, because if you're thinking about reducing square root of 3 over square root of 3, that would reduce to 1. And so 1 times anything is just the original number. But now let's go ahead and multiply this out. So we'd have 5 times the square root of 3 times the square root of 3. So in the numerator, I'd have 5. Well, if I do square root of 3 times square root of 3, those square root of 3's cancel out. And so I would be left with 5 times 3 over 2 square roots of 3, which is equal to 15 over 2 square root of 3. Now I could do a similar one for rationalizing the denominator, but I'm going to do one that doesn't involve a square root. Square roots are fairly straightforward, but let's look at rationalizing a denominator, which is the one you're probably more familiar with. But let's look at it where we have instead 3 over the cube root of 5. So what do I need to multiply by here? Well, let's take a little aside over here. I'm going to put it over here. And what do we know here? Well, I could, of course, use a calculator to do the cube root of 5, but that's not the point here. I wanted to figure out what this is. And so cube root of 5, well, if I had the cube root of 5 cubed, I know that would simply be just 5. So I want the cube root of 5 cubed. Well, what would that mean? I have the cube root of 5, so what would I want to multiply by? I'd want to multiply by the cube root of 5 squared, because then that would be the cube root of 5 cubed. So what I'm going to multiply the numerator and denominator by here is the cube root of 5 squared over the cube root of 5 squared. And then simplifying this, we'd have 3 times the cube root of, well, 5 squared, we'll go ahead and write that as 25, all over 5, because the cube root of 5 times the cube root of 5 squared, as we showed over here, is just equal to 5. Okay, one more example here of rationalizing a denominator. And this one here is where we have something like, let's for instance look at 2 over the square root of 5 minus the square root of 7. Now I want to rationalize the denominator here. Now what we're going to multiply by is what's referred to as the conjugate. And the conjugate is a fairly simple thing here. If, for instance, we have a minus b, the conjugate is a plus b. And of course, if we have a plus b, the conjugate is a minus b. Simply all you're doing is flipping the sign, and what you're going to then multiply by. And the reason is we want to do that, going back to some algebra here, we had a special product that you should be familiar with. that if you have a minus b times a plus b, you of course could FOIL it out, but this is just equal to a squared minus b squared. Okay, so using that, let's go back to the example here. So I'm going to multiply the numerator. Now I'm putting in parentheses because I'm not just multiplying by everything. I have an addition in here. So I have square root of 5 plus square root of 7 divided by, and I'll put a set of parentheses over here, square root of 5 plus square root of 7. Okay, so the numerator is pretty straightforward. This is just 2 square root of 5 plus square root of 7. And then the denominator, this would be divided by, well, remember it's a squared minus b squared, so square root of 5 squared is 5. 7 squared, square root of 7 squared I should say, is 7, so it'd be 5 minus 7. Now let's simplify this all the way here. So this would be equal to 2 square root of 5 plus square root of 7 all over negative 2, which this is then just simply negative square root of 5 plus square root of 7. Notice I still have the parentheses here because 2 over negative 2 is of course negative 1, but that applies to everything. Now we could just leave it like this as a final answer. If you wanted to expand it out, you could, but remember you have to distribute that negative sign into both things, so this would be negative square root of 5 minus square root of 7. Okay, there's one other quick thing here that we need to talk about in this review of radicals, and this is radicals and fractional exponents. And there's one quick property here. The property is that if you have the nth root of, I'm sorry, I want to write it backwards here. I'm just trying to be consistent with the other. You can write it anyway, but I'm just trying to be consistent with my notes here. If we have the nth root of x to the m power, this is equal to x to the m over n. So, quick example here. If you have the cube root of x to the 4th power, this would be equal to x to the 4/3 power. Another example, if you have the square root of x, well, remember what's the exponent on x when it's just there? That's 1, so this would be x to the 1/2 power. Now you want to be able to go both directions. Again, later math classes, this is critical to be able to go back and forth between these two notations here quickly. But one thing, as I said, you also want to go the other way. So let's suppose we had y to the negative 3/4. Well, first off, I'm going to rewrite that with a positive exponent. So this would be 1 over y to the 3/4. And then I'm going to convert that using a radical. So this would be 1 over, it's the 4th root, because that's what's in the denominator, of y cubed. So I encourage you to look over some of these, but those are just a quick review of some of the radical rules that we'll need to use in the course.